Table of Laplace transforms. This you need to remember. I mean, it can help you. Table of Laplace transforms. So, so let's write the function and the Laplace transform. So start with 1. Laplace transform 1 is 1 over s. That's very easy to find using the definition. Laplace transform t is 1 over s squared. Those you kind of need to remember. And then we have t to the nth power, which is factorial n divided by s to the n plus 1. And then we have sine omega t. Omega is a constant, which is omega divided by s squared plus omega squared. And then we have cosine omega t, which is s divided by s squared plus omega squared. And then we have the e function, e to the minus at. So if you have e to the minus at, it is 1 over s plus a. See the sign change. And then we have the Heaviside function ut minus a, which has e to the minus as over s. Actually, you have to be careful. We dividing the whole thing by s. Okay, so it is e minus a, divide the whole thing by s, not just the minus a's part. And then we have the first shifting theorem. It is e minus at eat ft. So if you get eat ft, the answer is you just get the Laplace transform of the function. You replace s by s plus a. So again, opposite sign. Okay, opposite sign. So it's a good thing to remember. But in the Heaviside function, it's the same sign. And then the second shifting theorem, which is u t minus a f t minus a, which is simply e minus as fs. So this is what we call the first shifting theorem, and this is what we call the second shifting. So these are useful when you try to find the Laplace transform and the inverse Laplace transform. So these are the kind of thing that you can remember, because it's not that difficult. If you remember them, it's easy to find those inverse and Laplace transforms. Okay, so and then there are some facts about these linear transforms. The Laplace transforms. One of the big fact is linear. This is a linear operator. Okay, it's a linear operator. What does that mean? If we have a sum like that, if you try to find the Laplace transform of the sum, it is simply the first one plus or minus, it doesn't matter, whatever. The same sign goes here, and then g. So that is the first condition. The second condition is if there is a constant, you can simply pull the constant out. So those two properties can make life easier because it just act like as we expected. So let's try to kind of do two problems from that. So let's do this one. Find the Laplace transform of find LF4. The first one is, let's say, if t equal to t minus e to the negative 2t plus sine 3t. So let's try to find the Laplace transform. So LF is it's a 2 times Laplace transform of t is 1 over s squared minus, this is the eat function here, a equal 2, so that means 1 over s plus 2. And this is sine, we know the table is omega over s plus s squared plus omega squared, so it's a 3 over s squared plus omega squared means 9. So that's the answer. I mean, you cannot do much with this, so we leave it like that. Let's do another one. How about this one? Let's say you have ft equal e to the negative 2t sine 3t. So if you have something like that, that's the eat function. So according to that, your answer is, what we can do, we first find the Laplace transform of the major function, the sine 3t. So we can do that first. It is 3 over s squared plus 9. And then what we're going to do, we're going to shift s to s, because we have that's the number, so that means plus 2. Okay, so when you have a, so remember the format, there's a negative sign here, but we're going to go with the plus sign. So that means it's going to be, you simply replace s with s plus 2. So if you do that, you end up getting 3 over s plus 2. You place s with s plus 2 squared plus 9. If you want, you can simplify the bottom. That's not a must. If you do that, if you expand and add 1, add 9, you get s squared plus 4s plus 13. So that's what you get. So that's the Laplace transform of that. Okay, so it's not that difficult, but this is how it works. Okay, now let's talk about the inverse Laplace transform. So we're going to define the inverse Laplace transform kind of in a like a interesting way. So inverse Laplace transform. So how we define inverse Laplace transform? We're going to say if the Laplace transform of a function is fs, if and only if, let's go backward and forward. If you take the inverse of fs is the ft, so that's the kind of idea. So you can transform backward. So I mean, that's how we define the inverse transform. That means if you know the Laplace transform, you can simplify the inverse Laplace transform. So let's do like 2 examples just to see how it works. So find the inverse Laplace transform. Let's start with this one. So the first one, inverse Laplace transform of 3 over s plus 2 minus 1 over s minus 1 squared. How we do this? It's already factored. Otherwise, we have to find partial fractions, but it's already given. So this is the linearity. So it is, you're going to take 3 out. So it's L inverse 1 over s plus 2. And here you can take the minus sign out. It is L inverse 1 over s minus 1 squared. Okay. Now let's see how we can do it. So the first one is easy. It is 1 over s plus a. That's one of the formula in the table. So that means this is simply 3 e to the minus 2t, opposite sign. Okay, that's s 1 over s plus a. Minus, how about the second one? When you want to do the second one, you first need to figure out, it's a shifting version. That's a shifted version. You want to figure out what is the base function here. The base function is 1 over s squared. If the base function is 1 over s squared, we know that 1 over s squared is corresponding to t. So we write t because that's 1 over s squared, because that's the base function. Here the base function is 1 over s squared, you see? And then you shift it. Then the shifting part comes. That means the e term comes. So in this case, the shifting part is e, but it is minus 1. So that means it is plus 1. So it's a plus 1 t. So that's what you get. Okay, so it's simple. So you need to figure out what is the base function. The base function is 1 over s squared. 1 over s squared is corresponding to t, and then you do the shifting. That means you multiply by e to the t. So that's the eat function example. Okay, so what I use here is, I'm going to write it here. So what I use here is, we know that if you have e to the minus at ft, it is simply f s plus a. So that's the one we use. Good. So let's do one more example. How about this one? let's say L inverse 3 plus 2s over s squared plus 4. So if you get something like that, what we can do, it's not directly something that we know. So what we can do, we can split this. We can split this into two fractions. So what are the two fractions? You can see that I'm going to take 3 out. L inverse. First one, I'm going to write s squared. So what is missing here? We know that this is very close to the sign, but if the sign, the square root of 4 is missing, that means 2 is missing. So what we do, we multiply and divide by 2. So that's what we do. We're going to multiply and divide. So we're going to multiply here by 2 and then divide here by 2. So that's the first one we do. Plus, because the linear, so things are easy, you take the 2 out. So we write L inverse s over s squared plus 4. So now we know all the both. So the first one is simply 3 halves sine 2t. Second one is 2 cosine 2t. So it's very simple. Okay. So but we have to break it into two, split, and then you can see it's right there. It's simply coming from the table. The next major method is the partial fraction method. So let's discuss that now. So the partial fractions method. Partial fractions method. So if you don't know much about that, there's a video that I did for my Calc 2 class. There, like I explained, like a vast a majority of questions, like in different types. So you can look at that, and there are like shortcuts, a lot of shortcuts to find the coefficients, and I discussed that there. So maybe you can look at that if you have enough time. Okay, yeah, that's the same one I posted earlier also. So let's do a problem like this. So let's say find the inverse Laplace transform of. So find the inverse Laplace transform. Inverse Laplace transform. So like let's say you get like a something like this. L inverse 2s plus 3 over s plus no. Yeah, actually, I'm going to let's slightly change the problem to this one, because this can be like a little bit difficult. That's what we can do as a second example. Let's do this one first. S plus 2 over let's say s plus 3 and s minus 1, something like that. But this is easy to do. Like if you have linear factors, those are very easy to do. So let's look at how it's going to work. So we can write the partial fraction decomposition. So s plus 2 over s plus 3, s minus 1 is identical to, we can write the linear factors. It's a over s minus 1. There's no order, just pick one. S plus 3. And then what we can do, we can multiply the common denominator. So we can write this one as s plus 2 identical to a times the other one plus b times the other one. You see, you get the other denominator. Now what you can do, just substitute. Okay, that's the easiest way to do this. So you can substitute. So you're going to substitute. Let's say you want to find a. So you try to make this term 0. So that means you plug in s equal 1. So you plug in s equal 1. If you do that, you get 3 equal a. 1 plus 4. This says that a equal 3/4. This is s plus 3. So 3/4. And then again we're going to substitute s equal -3 to find the other one. So negative 3, you're going to get negative 1 on this side equals, the first term is 0 now, and then from the other term b, you're going to get negative 4, because negative 3 minus a negative 4. So this says that b equal 1/4. So that's it. So you can find the two fractions, two coefficients. So that means if you go back and substitute a equal 3/4 s minus 1, b is 1/4 s plus 3. Good. So we have those two. Now what we can do, we can find the inverse now. So we can start with inverse, which is over s plus 2, s plus 3, s minus 1, which is equal by the linearity. What we can do, we can write this as a two separate ones. So it is 3/4 L inverse 1 over s minus 1. That's 1. The other one is 1/4 L inverse 1 over s plus 3. So now what's going to happen? S minus 1. We know the inverse of s minus 1, that is e to the t. So it is 3/4 e to the t plus 1/4 e to the minus 3t. So that's it. So you can see it's very easy to find. Only thing that we need is partial fraction decomposition. So if you know how to do that, everything looks great. Okay, let's do one more little difficult example. So B, let's do the other one that we we're trying to do. So let's say we have 2s plus 3 over s plus 1 squared s squared plus 4. So we know how to write the partial fraction decomposition for that. So this is, we can start with 2s plus 3 over s plus 1 squared, and then s squared plus 4. This is identical to, so when you have a repeated factor, linear factor, what we can do, we can start with the smallest one and then the next largest. So that's how we do it. And then plus this is s squared plus 4, and we know that b has the exact same format as a when they repeat, but here that's not the case. This is a irreducible factor, so we have write cs plus d. So that's how we write it. Now what we can do is the same thing. So we write 2s plus 3 identical to, write the missing term. Here the missing term of 1 of s plus 1 is missing, s squared plus 4 is missing. Here b only s squared plus 4 is missing. Here cs plus d, you can see s plus 1 squared is missing. Now what we're going to do, we're going to we do the substitution first and then the coefficient. That's the easy way to do it. So we're going to go with the substitution. So we can see that this term is common. So we're going to substitute s equal -1 to find b. So we substitute s equal -1. If you do that, you get 1 equal 0 plus b. If you plug in -1 squared, that means 1 plus 4. So you're gonna get so you can see you're gonna get b equal and then also this term is 0, so this says that b equal 1/5. So we already find the b value. Now what we can do, you can see that you can plug in anything else and directly find any other values, any other coefficients. So what we're going to do, we're going to go with the coefficients. So we always start with the largest coefficient that we discussed several times. So what's the largest coefficient? What's the largest term that you're going to go with? S. You can see s cube is the largest. So we're going to go with that. So there's no s cube term here. So that means it is 0. And then you can see you get a s cube term when you multiply these. So that means the coefficient is simply a. The same argument from the next one you are not gonna get 1, but from the last one you will again get this s squared s. So that means there's another s cube term, that means c. So those are the coefficients. That means a plus c is 0. That means if you know one, you can find the other one. Now what we can do, we can write an equation for s squared. So what we need is just 3 more equations, because we have 3 unknown. We need 3 more equations. I'm going to go with, because you know that all of them related with a. So because of that, because a has like is constant has a, s has a, s squared has a, s cube has a. So I'm going to go with not s squared. I'm going to go with s. Okay, coefficient of s. If you go with coefficient of s, it is 2 on this side. On the other side, you're gonna get from the first term, the coefficient of s is 4a from the first one, and then from the second one, there's no term, so that's easy. From the last one, let's expand this one. So if you expand s plus 1 squared, it is s squared plus 2s plus 1. So it's gonna help you to figure out what is the coefficient. So what is the coefficient of s? To get s, one way to get s is you can see you can multiply 1 with cs, so it's a c is a coefficient, and to get another s, you can multiply d with 2s, so that means 2d is a coefficient. Now what we can do, we know that a plus c is 0, so that means you can remove 1 of a plus c from this. So if you remove 1 of a plus c, you only have 3a plus 2d. So that's easier compared to the original one. And then let's go with the constant term. So if you get the constant term, you get 3 on this side. What is the constant here? 4a is a constant. 4b is a constant. And from the last one, you can see d is a constant. So now what we can do is, so we need 2 equations with the same variable. So to get that, what we can do is you can substitute for b in the last one. So if you substitute for b in the last one, what are you going to get? So you can see, if you substitute a b for the last one, you can see the b is 1/5. So it is a 4a. So this says that 4a. This says that 4a plus d, 4a plus d equal 3 minus 4b. But what is 4b? Which is 3 minus 4/5. That means 15 over 11. So that means you're going to get equation 4a plus d equal 11 over 5. Now what we can do is we can solve the last 2 equations, 4a plus 2d and 4a plus d. And if you solve those last 2 equations, and you can see that you can get a easily, because you can multiply the second one by 2 and then subtract the top one. So if you do that, so okay, again I'm just write the 2 equations here. So we have 2 equal 4a plus 2d, and here we have 11 fifth equals 3a, not 4a, 3a. And then we have 4a plus d. So what I'm going to do, we can solve these two. I'm going to multiply the second one by 2, and then you're going to subtract the first one. So once you do that, you're going to get 12 over 5th equal is 8a minus 3, 5a. So this is going to give you the a. So a equal 22. A equal, actually what do you get? 12 over 25. So a equal 12 over 25. That's what you get for a. And then we know c. Because of that, then c is simply minus a. So this is negative 12 over 25. So, and then we can find d from one of those equations. And then we can find d. So I'm going to write the value so you can verify. So this implies that D equal, just plug into one of those equations. So it is D equal 1115 over 4a. So 1115 minus 4a. So this is going to give you the D value, which is 725. Okay, so we find A, B, C, D, all four. Okay, that's the only part like taking time. Otherwise, just the method is easy. So then after we know all four, so then we can write this expression. So we had, I'm going to rewrite this one, 2s plus 3 over s plus 1 squared, s squared plus 4, s squared plus 4 equal, we had 22 over, it is 22 or a equal actually 12 over 25. So it is 12 over 25 1 over s plus 1, and then we had b is 1/5 1 over s plus 1 squared, and then we had 11, a negative 12 over 25 c, that's a c value, and the d was 7 over 25 over s squared plus 4, but you can split these two to get not the c, yes, to get a sine and cosine term. Okay, now we have everything we need. So the inverse of this 2s plus 3 over s plus 1 squared, s squared plus 4 equal, so so we're going to find the inverse of each term. So that means this is going to give you 12 over 25 L inverse. I'm just writing this one. This is not really necessary, but for completeness I'm writing it. And then 1/5 L inverse 1 over s plus 1 whole thing squared. The next one, what I'm going to split that into two. So we have negative 12 over 25 L inverse. The first one, which is s over s squared plus 4, which is a cosine, plus 7 over 25th L inverse 1 over s squared plus 4. So what we can do, we can multiply by 2 and divide by 2, that we can do. So that means your final answer is simply going to be 12 over 25 e to the negative t plus 1/5 t e to the negative t. That's the second one. How it coming from? Because s plus 1, that means 1 over s square, s plus 1 square, that means 1 over squared is the term, that means t, and the shifting is e to the negative t. That's a shifting term. And then we have negative 12 over 25, the cosine 2t, and then here what's going to happen is a sine 2 is missing, so you multiply and divide by that. So that means you're going to get 7 over 50 sine 2t. Okay, but this may be like little long to an exam, so you will get something you can manage. This is like little long compared to other problems. Okay, good, but I want to show you like how it works. It's not that difficult. Only problem is the how to find the partial fraction decomposition. Good, that's about that. And then let's talk about how to solve a differential equation using the Laplace transform method. That's the most important one. So solving differential equations using Laplace transforms method. Solving differential equations using the Laplace transforms method. So let's start with the Laplace transform of derivatives. Laplace transform of derivatives. we know these results, so the Laplace transform of the first derivative is s fs minus f0. Laplace transform of the second derivative is s squared fs minus s f0 minus f prime. You can see first term is positive, everything else is negative. That's something you can. So if you write the third derivative, so you can just keep doing it. If you write the third derivative, which is s cube fs minus the power of s goes down, so that means squared f0 and then s f prime 0 minus s double prime 0. So you can see all the terms after the first terms are negative. So that's something you can remember. Okay, these terms are negative. Okay, and then so you can continue like that. So you can have the general one. So it is a Laplace transform of f to the nth derivative. So the nth derivative is Sn fs minus s to the n minus 1 power f0 minus s to the n minus 2 power f prime 0, like that. And then you're going to be f to the n minus first derivative 0. Okay, so that's the idea. So you can see that except the first term, everything else is negative. So there's a negative sign. Okay, all negative. Only the first one is positive. Good. So now let's see how we can use this to solve a differential equation. So let's do solving differential equations. So let's look at this example. So solve x double prime minus x prime minus 6x equal, let's say 5e to the negative 2t, along with x0 equal 1 and x prime 0 equal negative 2. So if you get something like that, so what we normally do is we can take the Laplace transform of the equation. That's how we're trying to do, and then we can use the initial conditions given. So the answer, so let xs equal the Laplace transform of the expected solution. And then what we can do, take the Laplace transform of the equation. So taking Laplace transform of the equation, you're going to get s squared xs minus s x0, these are small one, minus x prime, that's the first term. The second term says minus, there's a minus sign, so let's plug in here. So s xx minus x. So it's a good idea to write this one to avoid errors. And then minus 6xs equal Laplace transform of that term is a 5, and it's a eat function, so it is s plus 2. So that's what you get. Now what we can do, we can substitute the conditions that we know. We know that this is this equals to 1, this equals to 1, and this equals to a negative 2. So if you plug in that, then you can bring, so you have a negative s term, you can bring the other side, and we have negative 2, so it becomes positive 2, and positive 1, so it's 3. So we have negative s plus 3, so you can bring it to the other side, take the common, so we have s squared here, and then we have minus s, and then we have negative 6 xs, and you can see this is exactly equal to the characteristic equation, but with the s, not the lambda but the s. So that happen always. And then now we're gonna bring the other terms to the side, so we have s minus 3 plus 5 over s plus 2. Now what we can do, we can divide by that. And then you can see this we can actually factor. What are the factors of this? The factors are s minus 3 and s plus 2. Those are the factors. So let's divide. So when you divide, what's going to happen? We have s minus 3 here, and then we have s minus 3, s plus 2 plus 5 over. So we have s minus 3. We have s plus 2, and there's another s plus 2 already over there. So that means this can be s plus 2 whole thing squared. And the interesting thing is sometimes, see, this get cancelled. So it simplifies well. So we only need to find one partial fraction. But otherwise, what we're going to do, we're going to simplify this here. So we normally what we do here is we simplify this. We simplify this before we find the partial fraction, so that it's going to make the calculation much easier, because it's going to be an internal calculation. That calculation is going to take care of most of the terms. So it's always a good idea to simplify this first. But here you can see we don't need that because that term cancels. So we have like nice one already. So we can separate those two terms. Okay, so what we have is 1 over s plus 2. So we leave that there because we already know the inverse of that. And we only need to find the partial fraction of this term, s minus 3, s plus 2 whole thing squared. Normally what we do, we're going to simplify this because it's going to make the calculation easy. So let's try to find the partial fraction of that. So now we're going to go with the partial fraction of that. So it's 5 over s minus 3 s plus 2 whole thing squared, which is equal to a over s minus 3 plus b over s plus 2 plus c over s plus 2 squared. So we're gonna and then after that we're gonna get 5 equal a, the missing term. Missing term is s plus 2 whole thing squared. In the next one, the missing term is 1 of the s plus 2 is missing, s minus 3 is missing. Last one, only s minus 3 is missing. So we can use a substitution technique now. Always use substitution first. So we can substitute, let's say s equal 3. If you do that, you get 5 equal, you can see plug in 3, this goes away. So you get a. So a, if you plug in 3, this is s equal 3, so it is 3 plus 2 squared plus 0 plus 0. This can give you a equal 5 over 25, so 1/5. That's a. Now we're going to substitute. Let's try to find what is the other common term. You can see this is common, see? So that means you can find c. So you plug in c equal -2. So you plug in c equal -2. 5 equal is a 0, another 0, and c, if you plug in -2, this is -2, -3. This can give you 5 divided by 5, the c equal -1. Okay. And then so we only need to find one more. What we normally do is equate the coefficients of the largest term. Remember that, okay? Because that's going to make the calculation much fast. So coefficient of the largest term. What's the largest term? S squared. So we're going to go with the coefficient of s squared, the largest term. So it is 5 largest degree. So you can see how to get a squared term. The first one going to get squared term, the coefficient is a. In the next one, when you FOIL, you get s squared b. So that's the next one. Since we already know a, we can find b from this one. So this is that b equal 5 minus a. So that means no, actually. So what I did, there's no 0 here. So there's a problem here. So you can see there is no s squared term. So this is 0 on this side. Okay, there's no s squared term. So it's 0. So you get b equal minus c. So since we already know a, so it is negative 1/5. Sorry for that. Okay, so it's 0 because there's no square term on this side, so it's 0. So you get a b3 like really quickly. Now what we can do, we can substitute that. So that means so is 1 over 5 over s minus 3 s plus 2 squared equal, you can write equal now, it is 1/5 s minus 3 actually let's write the s term. It's not this one because we already know yeah, so let's write the s1, it's very important. So if you write s term, so what do you get? So excess which is 1 over s plus 2 plus the partial fraction of these. Okay, so we're gonna have the partial fraction now. This is 1 over s plus 2 we had already. So let's try the partial fraction here. So it is 1/5 over 1/5 of s minus 1/5 of s minus 3. So we have minus 3. That's a, and then we have b. B is negative 1/5 over s plus 2, and the c which is negative 1. So it is negative 1 over s plus 2 squared. That's what you get. And you can see that you can combine these two. So they're going to simplify. So they're going to simplify. So you're going to get, so you're going to get 4/5. So we have 4/5 s plus 2 plus 1/5 s minus 3 minus 1 over s plus 2 squared. So we can find the xt now. So xt is simply, so I just wrote like completely, but some steps you can ignore. Okay, not really necessary. So this is the inverse of this. So we're gonna go term by term. So the first one says it is 1/4 e to the negative 2t. Next one says 1/5 e to the 3t. The next one is, you can see it is the base function is 1 over squared, that means it's a t. E to the shifting is negative 2t. So that is the solution of the differential equation. This one is not that long. It like kind of came quickly. Even like it's not that difficult to find the partial fraction decomposition for that. So this is a kind of good problem, especially for a final exam. Good. Next we can talk about the convolution method. So let's discuss the convolution method. Convolution method. So we know that the Laplace transform is linear. That means if we have a sum, we can write this one as LF plus LG. So we can do that. But if we have a product F times G, this does not equal to the Laplace transform of F times Laplace transform of G. So there's no such result. So instead we have what we call the convolution. So let's say, let's look at the definition. So what we call the convolution product. Convolution product. So the convolution is defined as an integral. So the notation is star. So f star g, that's the convolution of f and g. So which is from 0 to t. What we can do, let's introduce a new variable called tau. So it's f tau g t minus tau. So t is the variable sitting there, and d tau. Or you can even switch the order. So you can say, you can put the t minus tau for the first one, and then g tau for the second one. The interesting part is you get the exact same answer from them. So in other words, this means that this product is so you can switch the two. So that means it is commutative. So you can write it like that. That's what it means. You can switch the order, you still get the same answer. So now the question is, we put t minus tau for the easy one, so that is easy to integrate. So that's how you're gonna pick it. So whatever the easy one. So we're gonna see when you look at a problem, it will be clear what we mean by easy one. And then we have this major result. So the theorem is that it says, let's say f g are piecewise continuous, and exponential order, and the exponential order and of exponential order. We need that to guarantee that the Laplace transform exists. Then what happened? The Laplace transform of the convolution product f star g is simply the product of the Laplace transform of f and g. So in other words, we write this one as fs times g. This is just the product. So this is the major result. This is very useful. So that's what we have. So if you look at the convolution, Laplace transform of the convolution, you're going to get the product of the Laplace transform. So the benefit is, this is very useful when you want to find the inverse. So that means, so let's try this as a knot. So that means, so if we have an inverse of a product of two transforms, if you know that the two functions, what are the two functions are, just take the convolution. So that's the idea. So this might be much faster compared to partial fraction or other techniques. So that's how we can use it. So useful when finding inverse. Useful when finding inverse Laplace transform. So let's look at that in a problem. So let's try to do this too. So example, find the inverse Laplace transform. Find the inverse Laplace transform. So let's do the first one. Let's say L inverse 1 over s plus 2 times s squared, something like that. So we know how to do this one using partial fraction method. We write the form, find the ABC, because there are three terms now, and then invert. But how to use the convolution? So we know that, so we're going to kind of try to identify. So we can write this one as 1 over s plus 2 times s squared. So we isolate that. Now we can see this function corresponds to e to the minus 2t. This one corresponds to t. So those are the two functions. And then if you take the Laplace transform, that's what you get. So that means, according to the theorem, this is simply the convolution between those two functions. So that's the idea. Just take the convolution of those two. So now what we can do, we can use the definition and try to find it. So the question is, which one we're going to put t minus tau. So when you have exponential function, it's always a nice idea to put the t minus tau to the exponential function. So we're going to do that. So it's 0 to t, e to the negative t, we put t minus tau here for the exponential function. Other one is just become tau d tau. So the reason is, you can see you can pull out e to the negative 2t because that's a constant now. And then 0 to t, e to the negative, not negative, it becomes negative positive because you can see there's a negative. So e to the 2t tau d tau. So this is a very easy integral using partial integrating by parts. So let's do that. So it is e to the negative 2t. Now we can use integrate by parts. So we can use the di method for this one. So let's use the di method. d and I. So we're going to say for the d we put tau, I we put e to the 2 tau. So take the derivative 1, take the integral 1/2 e to the 2 tau, take the derivative 0. So that means 1/4 e to the 2 tau. And then what we do, we multiply plus minus. So that's what we get. That means the answer is simply we're going to multiply the 2, so it's a 1/2 tau e to the 2 tau, and then minus you get 1/4 e to the 2 tau, and then we can evaluate that. So let's change that. We can evaluate that at t and 0. So that's it. So that's the answer. So what we get? So you're gonna get e to the negative 2t. When you plug in t, so you get 1/2 t e to the 2t, and then minus 1/4 e to the 2t. And then when you plug in 0, the first one is gone, the next one becomes simply 1/4. And then what we do, we will multiply by e to the negative 2t, so you get 1/2 t minus, no, plus, yeah, so it's going to be plus 1/4 good, 1/4, and then we have no, that's actually, so it is negative because we multiply negative 2t with 2t, so you get negative 1/4, and then the last term gonna be plus 1/4 e to the negative 2t. So that's the answer using the convolution method. So it looks like it's a little faster compared to the partial fraction because we just need to evaluate a simple integral here. Good. Good. So let's try to do one more. So let's do this one. So the inverse Laplace transform of 3 over s squared plus 4. So this one, if you do the regular way, it's a little lengthy, but let's see how it's going to be now. So what we can do is we know that if you look at s squared plus 4, that's related to the sign. So what we do, we take 2, we multiply and divide by 2. So this is L inverse. So we're going to arrange it. So 1 over s squared times 2 over s squared plus 4. So we can write it like that. Now you can see this is t, this is related to sine 2t. So we have the two functions. Now what we need is, according to the theory, this simply becomes 3/2, that's there, t convolute with sine 2t. So that's what you get. Now what we can do, we need to find the simple convolution and you get the answer. So that means this is equal to, so we have, again we can use the di method for that. So the d and the I. So d, first let's write the integral representation is a 2/3, 3/2, 0 to t. I'm going to put t minus tau for the first one, and then sine 2 tau d tau. So this one we can use do using the di method. So t minus tau goes here, sine 2 tau goes, the tau is the variable, so we take the derivative, t is a constant, so you get negative 1 here, and the other side you get negative 1/2 cosine 2 tau, and then take one more derivative, 0, so so cosine, that means you can divide by 1/2, so it's a negative 1/4 sine 2 tau, so plus minus, so we can write that now. So you're gonna get, so let's plug in that. So we know the two product here, so let's plug in that. So it is 3/2. The first one is negative 1/2 t minus tau cosine 2 tau minus 1 is a because we have 3 minus signs, so it's minus 1/4 sine 2 tau. We can evaluate that at t and 0. So if you evaluate, if you plug in t, the first term is 0. And then if you plug in 0, so you get t half. And then from the next one, when you plug in 0, you get 0. When you plug in t, you get negative 1/4 sine 2t. And then finally, if you multiply it through, you get 3/4 t minus 3/8 sine 2t. It looks like simple compared to the partial fraction method, a little lengthy. So like it's up to you, like whether you want to use the convolution or partial fraction method when you get a problem, unless it says that use the convolution. So that's the kind of idea. So how about this one? So how about this Laplace transform? So this is another example. So find the Laplace transform of the integral from 0 to t sine 3 tau deta. So you can see that this is a convolution problem. What happened? Why you don't see the t minus tau term? Because that's a constant term. So that means it is simply convolute with 1. So that's why you don't see the t minus tau, because you can put the t minus tau to the constant. So that means this is simply the convolution between 1 and sine 3t. So if you do that, 1, so that's a convolution. So actually we do write it like that. So this is the convolution of this, like this, the convolution between 1 and sine 3t. So by the product, this is the convolution of 1 times the convolution of sine 3t. So if you use convolution, Laplace transform 1 is 1 over s times 3 over s squared plus 9. So if you write as just one single expression, s times s squared plus 9. So so we can do that. So like sometimes it's not really visible, what is there. Yeah, so that's a good one. And then so we can use convolutions if you want to find the inverse. Okay, so let's put it off inverse. So we can say use convolution. Not a must, but you can. Okay, use convolution when finding inverse. Finding inverse Laplace transform. So let's go to the next topic. That's the Heaviside function. Heaviside function and switching. So we talk about the switching. When we have a piecewise function, you can use this as a switch. So let's go with the definition of a Heaviside function. Or unit step function. That's the other way. So if you look at the graph, it looks like that. So what's going to happen until 0 is 0, and then at 0 it's going to jump to 1, and it stays at 1. So that is what we normally write as ut at 0. And then we have the shifted version of that. So let's say it's going to jump at a. So until a is 0, and then at 1 at a is going to jump and it stays there. So that is the Heaviside function shifted by a. So it is ut minus a. This is 1 at that point. So that's the function. Good. Now so the Laplace transform of those. So we have the Laplace transform of the Heaviside function. So Laplace transform. So we have Laplace transform of u t minus a equal e to the minus a s over s. So that's one. It's very useful. It's very easy to show this one. Just use the definition. And then we have also second shifting theorem. Second shifting theorem. So what it says that the Laplace transform of u t minus a times f t minus a. So they have the exact same format, t minus a, t minus a. So see that t minus a term and t minus a term. So what's going to happen? This simply become e to the minus as. So they have the exact same format again, minus as times the Laplace transform of s. So that's what we call the second shifting theorem. Now let's try to use this to find an inverse Laplace transform of a certain function. So let's do this one just to see how it works. For example, find the inverse Laplace transform of this one. So L inverse s plus 3 over s squared plus 4 e to the minus 2s, something like that. So let's say you have this one. So it's clear that that is the exact same format that we have the second shifting theorem version. So what we're going to do, we're going to shift this first. So we can write this one as L inverse. We can go with s first. So s over s squared plus 4 e to the minus 2s. And then look at the next one. The next one we have 3, but we actually need 2. So we can do that 3 halves, L inverse, 2, and then we have s squared plus 4 e to the minus 2s, like that. Now we can see this is the cosine 2t, this is the sine 2t. So what we want to do is from that we need to just shift this. So that means the answer is you're going to shift by 2. So it is u t minus 2, the cosine 2 times t minus 2, plus we have that 3 halves again u t minus 2 sine 2t minus 2. So that is the inverse Laplace transform. So that is how we use that idea. When you have a e to a function like that, it's just a shifting. It just is a second shifting theorem for that. Now let's look at how we use this for switching. So let's do a problem like this. Let's do rewriting a piecewise function using switches. So rewriting a piecewise function rewriting piecewise functions. Okay, so let's look at the idea like a problem like this. So example, so let's say you have a function like this. So let's say rewrite using a Heaviside function. So what we can do, let's say ft. Let's say you have a piecewise function like this, t minus 1 on the interval 0 to 1, and then sine t after that. So if you look at the graph, this is how it looks like. So from 0 to 1, it is a t minus 1. So that's a t minus 1 function. This is going to go with 1, negative 1. And then what happened? it's going to jump to the sine function at 1. So sine 1 is a number somewhere, and then it's going to follow the rest of the sine function. So it's going to go like that. So that's the idea. After 1, it's going to follow the sine function, but until then it's t minus 1. So these are what we call piecewise function. So this is a nice piecewise function. So the question is how to write this one as a using as a single function using a heaviside function. So what we can do, we can add a switch here. So you can see we want into the switch for the first interval from 0 to 1. The is switch on at 0 and then off at 1. So that's what we do. And the next one gonna switch on at 1. So that's the idea. So that means we can write this one as, we're gonna multiply just by the switch. So we have the function t minus 1. We're gonna multiply by the switch. So the switch here is ut minus 1, and then plus, that's the first one, that's going to switch on only in that interval. The next one is sine t, that's you're going to switch on after 1. That means you multiply by t minus 1, the function, whatever the function, so sine t. So that's how you write using switches. And if you want, you can even combine them into one function. For example, there's only one ut function, so that means you can write this one as t minus 1 times ut, and then there are t minus 1 function, there's a t minus 1 here, and then also sine t, that's positive. So what we're going to do, we can write this one as plus 1 minus t plus sine t times ut minus 1 as two separate u functions. So that's how you write this using switches. Simple idea, you're going to switch on at the first node, off at the other node. So that's the off part, that's the on part. Yeah, just pick the two values. So that's the idea. And then after, what you can do, you can use this theorem to proceed with this. So let's just solve one example to see how it works. Probably we can combine this and the convolution in this problem. So let's solve this one. So solving a differential equation, with a piecewise input, solving a differential equation with a piecewise input, like that. So the example is this. So let's solve this one. Let's say x double prime minus x prime minus 2x equal ft, along with x0 equal 0 and x prime 0 equal 0, just to make things easy. So where, let's say ft equals something like this, 3t 0, t greater than or equal 1 and 0 otherwise. So that means if you look at the graph, this is how it looks like. So what happened until 1, it is 0. At 1, it's exactly start with 3t graph. So that's that. It's going to follow that. So that's the how the ft function look like. At 1, it jump to that, and until there is 0, just stay 0, so no input, and all of a sudden it's going to exert a some input like voltage, current, something like that, which changes linearly. So now what we do, if you get a problem like that, we first use the switches to write it. So you can see you want to switch on at 1, so that means this is simply 3t ut minus 1. That's what happened. 3t times ut minus. This is switch on at 1. So the goal is to use the second shifting theorem, because you're gonna try to use because there's no other way to do it. You can directly use the theorem like a integral, that you can do. You can use the integration and you can integrate this one. That's one way to do it. But if you use the second shifting theorem, you have to write this in t minus a form, t minus a form. So a in this case is 1. So let's do that. So what we're gonna do, we're gonna subtract and add 1. So we write this one like this. It's a trick here. So what we're gonna do, we'll start with t, we're gonna subtract 1 and add 1, and then ut minus 1. Now if you distribute with the first one, you get t minus 1 ut minus 1. In this case, the function is ft. That's the function, ft equal t. And then the other function is simply 3 times ut minus 1. We know the Laplace transform of that. So that's how we find. So we're going to simply get the 2 Laplace transform of these two if you write it like that. So that's the point. We write it in this form. Okay. So the answer here, because you're writing ft in this form, so we write it like that. Now we can simply find the Laplace transform. So if this is the case, then the Laplace transform of ft is so it's a 3 times the Laplace transform of t minus 1 ut minus 1 plus 3 times the Laplace transform of ut minus 1. And we know that there are formulas for both. So the first one is simply 3 e to the minus s over the function is 1 over s squared. That's the Laplace transform of 1. Why 1? Because that's the function. Plus the second one, it is 3 times e to the minus s. That's the second one. So what we can do now over s actually. So there's s. So now what we can do, take the common denominator. Common denominator is s squared. So we can write this one as 3s plus 3 over s squared e to the minus s. So we can write it like that. Okay, so that's the Laplace transform of the signal, the input function. Now let's take the Laplace transform of the differential equation. So we have the inverse, not the inverse, the Laplace transform. No, yeah. So let's do it like that. So let's say taking the Laplace transform, taking the Laplace transform of the differential equation, we're gonna get s squared sx. There are no initial conditions, so only the sx terms, minus and then minus 2sx. So that's what we have. On the other side is the fs that we already know. So this is s squared minus s minus 2 times sx. On the other side it is 3 s plus 1 over s squared e to the minus s. So what are the factors of this? S minus 2 and s plus 1. So that means when you divide, s plus 1 get cancelled. So you simply get sx. S plus 1 get cancelled, so you get 3 over s squared s minus 2 e to the minus s. So if you have e to the minus x, what we normally do is first try to find the Laplace transform of the rest of the function, and then use the second shifting theorem to transform. So that's what we normally do. So to find the inverse Laplace transform, let's use a convolution now. So we need, let's see, we need the inverse Laplace transform of 3 over s squared s minus 2. So this is L inverse. We're gonna break this 3 over s squared times 1 over s minus 2. So this simply says that it is 3t convolute with e to the 2t. So that's what you get. Now we can use the definition. So 3 times, when you have exponential function, that's where we're going to put the t. So it is 0, t minus tau. So it is tau e to the 2t minus tau d tau. So we did this a lot. So now we know what to do with this. So it is 3e to t, we take it out, 0 to t, tau e negative 2 tau d tau. So that's what you get. And then we can integrate this one using the di method again. So we have tau e to the negative 2 tau, so 1, 0, 1 half e to the negative 2 tau, and then we need one more, so it is 1/4 e to the negative 2 tau. We multiply these two and multiply those two, plus and a minus. So now we can write the answer here. So this is simply going to be 3 e to the 2t times, let's try the first product, so it is 1 half tau e to the negative 2 tau. Next one is 1 half negative 1/4 e to the negative 2 tau. And then you're going to go with t and 0. So if you plug in the 2, so what happened is, so you have 3e to t. Let's plug in t, so you get 1 half t e negative 2t. And then when you plug in 0, is gone. And from the other one, when you plug in t, you get 1/4 e to the negative 2t. When you plug in 0, it's positive 1/4. So that's what you get, and multiply through. So you're gonna multiply by that. So 2t get cancelled because the negative sign. So you get, the first one is negative 3 halves t. Next one is 3/4, and then next one is plus 3/4 e to the 2t. So that is what you get as the inverse Laplace transform. Now what you want to do is you want to use the second shifting theorem to shift. Okay, so by the second shifting theorem, so by the second shifting theorem, we have xt, which is the L inverse of 3 over s squared s minus 2 e to the negative s. So that means you're going to shift by -1. So that means everything would be so we get the function first. So this is the function. So we're going to go with the function. You replace t with t minus 1. Negative 3/4, there are no t here. And then 3/4. We have e to t minus 1. And then everything multiplied by the heaviside function ut minus 1. So that is the final answer for that problem. Yeah. To get the same answer, you can also use the partial fraction method as well. Okay. So you may also use the partial fraction method. Good. So now let's try to go to the last topic of Laplace transform, that's what you call the Dirac delta function. So let's talk about that. So the Dirac delta function impulse response. So the Dirac delta function. Dirac delta function and impulse response. Impulse response. So let's talk about what's the Dirac delta function. There's the impulse, so like the sudden force acting like a at a single point. That's the kind of idea. So we can write this one as delta t. So like a so it is acting at the 0 point, so it's called delta t. And then we have the shifted version of that. So the shifted version is at a. That's impulse at a. So that's it. And then everywhere else it's 0. So this is what we normally write as delta t minus a. So impulse at a. And then we have the Laplace transform of that. So the Laplace transform, the first one is delta t, that is 1. And then the Laplace transform of the shifted version delta t minus a, which is e minus as. So this is useful to remember. And if you plug in a equals 0, you get the other one. Good. I mean, that's it. So let's try to see how we can use this to find the inverse Laplace transform. So let's do a problem like this. Find the inverse Laplace transform of, so let's say find the inverse Laplace transform of the first one, L inverse s plus 3 over s plus 1. And you can see that this is not a proper fraction. So if you have improper, this is what we call improper fraction. What you can do is you can do the lone division and find the remainder and the quotient that you can do. Also, you can use some kind of tricks here. So that's much faster. So what we're gonna do, we try to create the bottom term in the top. That's the argument. So how we do that? We can write this one as s. We can write this one as s plus 1 plus 2 over s plus 1. Then we can write with this and with the other one. So we're gonna separate this now. So we can write this one as so L inverse s plus 1 over s plus 1 plus 2 over s plus 1. So that means this is simply L inverse 1 plus 2 over s plus 1. We know that the 1, that means the delta function, this is delta 1, it's a delta t, that's 1, plus 2 over s plus 1 means e to the negative 1t, because a equal 1 in this case, so 2 e to the negative t. So that's what you get. So that's how we find the inverse when you have an improper fraction like that. So the delta function comes into play in this case. So let's just do one problem also, another problem like that. So how about this one, L inverse? So let's say s, let's look, s e to the minus 2s plus 3 over s plus 1. So what we can do with this? Again, we can split this. So this one we can write as L inverse. So you can see we have s here. So we can do the same idea. So we can write this one as, we try to create the denominator. So it's plus 1 minus 1. e to the minus 2s plus 3. So this is over s plus 1 over s plus 1. You can write it like that. Now the same trick. So you can go with s plus 1 with the bottom term. So that means we can write this one as, if you go s plus 1, you simply get e to the minus 2s. If you go with minus sign, you get minus 1 over s plus 1 e to the minus 2s, and then we have this 3s plus 1. Now we go term by term. So the first one is simply delta t minus 2, where a is in this case 2, so it's a t minus 2. The next one is so we have to use the Heaviside function for this one. We find it and then we can transform that. You can see you have to the function is 1 over s plus 1. That means e to the minus t. You replace t by t minus 2 and then multiply by the shifting function as well. So it is e to the minus t. You replace t by t minus 2. So replace t by t minus 2. Multiply by ut minus 2, that's that, and the next one is simply 3e minus t. So that's the kind of idea. So this is how we can do it when you have a term like this. This is special case. So you either get this or you either get that. So it's gonna come with one of those. Good. Now let's try to solve one problem using this method. That's the end of Laplace transform techniques. Let's just do one example. So find the impulse response. Find the impulse response. Find the impulse response of a system. Okay. So for example, let's say, so this is the question. So I'm going to give the exact same wording. Find the impulse response, or simply say solve the differential equation. Find the impulse response of this one, x double prime minus x prime minus x equal, let's say 4 delta t minus 3, something like that. Okay, so where this is coming from, and also with x0 equals 0 and x prime 0 equals 0, just to make things easy. So where this differential equation coming from? So this is a kind of situation. Let's say you have a mass on a table which connected to a spring with the friction stable. Now what we're going to do, you're going to give a sudden impulse to one direction at the time t equal 3. So you wait and just give a sudden force in one direction. So that's the kind of situation. So now you get a differential equation like that. So let's try to solve and see what's going to happen. So what we normally do, so just the same procedure. Take the Laplace transform. Take the Laplace transform. So you get s squared sx plus sxs minus xs equal, okay, let's write the Laplace transform of that. We know that just the e minus whatever the number is 3s. Very simple. Initial condition 0, so you don't get that. So here we have s squared. There's a minus sign. Yeah, this is minus s squared minus s minus 1 times sx equal 4e negative 3s. So sx equal 4e minus 3s over s squared minus x minus 1, and you know that you can see that there are no factors for the bottom function. So what we can do, we can go with the completing square technique. So let's do that. So it is 4e minus 3s. What's the completing square here? So it is s half of the s term, half of the coefficient s term, that is 1/2. We can square that, so it's going to give you the first two terms, and it also give 1/4. But there's you have to get -1, so that means you subtract 1/4. So if you subtract 1/4, this can be 5/4. So that's what you get. Now this is you can see this, you can invert. So what's going to happen now is